All right, so let's start. So today I'm going to talk about chapter 16, and this is about the static electricity. Okay, so here you are basically learning about electric charge and electric field. Okay, all right, so let's start with this experiment. Okay, so in this, in this picture, you see that a comb is attracting small piece of paper. And you probably, at least some of you probably have done this experiment in your childhood. Okay. Also, you may have experiencing of getting shock when you touch a metal doorknob or a car handle. Okay. So what happened in these two cases? Okay, so to understand this, let's work on this simulation. Okay, so when you walk on a carpet, okay, or when you rub your hand with your sweater, so you see that charge goes from one object from the carpet to your body. Okay, now you see that you are now a more negatively charged object. Now when you touch the metal, okay, you see that you get a shock. Okay, so what happened here and also in this picture, okay, charge basically goes from one object to another object. Okay, and you already know what charge is, right? So in chapter 13 you learn about atom, and you probably remember atom consists of positively charged proton and negatively charged electron. Okay, so we'll be learning a little bit more about electron and proton here in this chapter. Okay, all right, now let's learn some rule about charge. The first one is charge cannot uh, charge charges are neither created or destroyed. Okay, so you cannot create a charge or destroy a charge. Okay, but they can be redistributed. Okay, so for example, so let's consider this picture. So for example, when you rub a glass rod, so here this is a glass rod with silk. Okay, so charges basically goes from one object to the another object. Okay, that means they are redistributed, and the total number of charge in any interaction is conserved. Okay, so one object basically gain charges and another object basically lose charges, but the total sum before and after the interaction is the same. Okay, so that's why we call electric charge is conserved in any interaction. Okay, all right, now as I already mentioned that there are two types of charges, positive and negative. Okay, and the rule is like charges repel and opposite charges attract. Okay, so here in this picture you see that negative is going away from the negative, positive is going away from the positive, and negative is going toward the positive. So you see that opposite charge attract each other, like charges repel each other. Okay, so you can also see this here in this simulation. Okay, so here you see that we have a neutral sweater and neutral balloon. Okay, neutral means they have same number of positive charge and negative charge. Okay, now if I rub the balloon with sweater, you will see that charge goes from one object to another object. Right, so you see that balloon is now more negatively charged and sweater is now more positively charged. Okay, and if I release the balloon, because positive and negative attract each other, you will see that balloon is going toward the positive charge. So you see that. So now you know that opposite charges attract each other, same charge, like charges repel each other. Okay, a neutral object does not do anything. So you see that here we have two neutral object and nothing is going on here. Okay, all right, Now, little bit more about the atom and charges. Okay, so here in the left hand side you see a model of atom. Okay, and you already know that the diameter of an atom is this. Okay, in chapter 13 you learn about that. Okay, the diameter is 10 to the power minus 10 meter. Okay, and at the center, so this is the center is the nucleus, and in this small nucleus we have positively charged proton and neutral neutron. Okay, and outside, so here you see that outside we have the electron. Okay, and the nucleus size is very tiny. Okay, tinier than atom. So atoms uh, radius is 10 to the power minus 10, and you see the diameter of nucleus is only 10 to the power minus 15 meter. Okay, so even it is small, okay, because the proton and neutron are heavier than electron. Most of the mass of an atom are concentrated at the center, okay, at the nucleus. So here you see that 99.9% of the atom's mass is concentrated at the center, okay, because center contains the most of the mass. Okay, so here in the right hand side you see what's the mass of proton, neutron, and electron. Okay, so you see that mass of proton, which is positively charged, is this. Okay, 1.673 times 10 to the power minus 27 kilogram. Okay, neutron is neutral, that means no charge, and mass is almost same as proton. Okay, so I mean the order is, you see the order is 10 to the power minus 27. On the other hand, the electron, which is negatively charged, and the mass of electron is this 9.101 times 10 to the power minus 31 kilogram. Okay, so you see that this is 2000 times less than um, proton and neutron mass. Okay, so electron is less massive than proton and neutron, and that's why most of the mass of an atom is at the nucleus. Okay, an atom contains a equal number of positive and negative charge. Okay, and that's why atoms are neutral, always neutral. Okay, because it has so for example, here in this picture you see that it has 3 positive charge and 3 negative charge. So 3 plus 3 minus 3 equal to 0, so that's why it is neutral. Okay, although it has electron and proton, but the total when you combine, okay, the negative charge is cancelled with positive charge, so that's why the total charge of an atom is equal to 0, and hence it's a neutral. Okay, so you can see here you can build basically an atom. Okay, let's build a carbon atom. Okay, carbon basically contains 6 proton and 6 neutron and 6 electron. Okay, so so here I'm adding the protons. Okay, so you see the proton, I mean the nucleus, now we have 6 proton, now it needs 6 neutron. Okay, so you see now it has 6, now it needs 6 electron. Okay, okay, so you see that it has 6, so it is neutral carbon atom. Okay, all right, so I mean not only carbon, all atom uh, uh, I mean all atom have equal number of proton at the center or at the nucleus, and the same amount of electron in the outside. Okay, all right. we go back to this simulation later one more time. Okay, now let me talk about the charge. Okay, the numerical value of electron and proton charge. So the electron and proton have the same amount of charge, and we represent it by using E. Okay, okay, and the value of E is this. Okay, 1.6022 times 10 to the power minus 19 coulomb. Okay, so C is coulomb. Okay, we'll be learning about coulomb later. Okay, so I mean the unit, standard international unit for charge is coulomb. Okay, so both electron and protons charge is this. Okay, although for proton we use a positive charge, so normally we write plus E for proton. Okay, and minus E for electron. Okay, so proton is positively charged. Okay, and electron is negatively charged. So proton charge is plus 1.6022 times 10 to the power minus 19 coulomb, and electron charge is minus 1.6022 times 10 to the power minus 19 coulomb. Okay, and this is the smallest, I mean the numerical, this numerical value is the smallest possible charge. Okay, and all other charges are integral multiple of this charge. Okay, and that's why we call it electric charge is quantized. I mean, we cannot have the continuous charge. Okay, all the charges are integral multiple of these. Okay, so if we call it E, then all other charge will be 1E, 2E, 3E, or plus minus. I mean, it could be plus or minus 100E, 1 billion E, and so on. Okay, so that means the electric charge is quantized. Okay, now if we break a proton or a neutron, okay, so when we break a proton or neutron, and then we can see that proton and neutron are basically made of something called quarks. Okay, and quarks has charge which is less than the electron charge. Okay, but that is some higher order things which we are not going to discuss in this course. Okay, normally we discuss this kind of thing in particle physics. Okay, but yeah, I mean less than this charge is possible. Okay, when we break a proton or a neutron. Okay, proton are made of some quark, up quark, two up quark and down quark, whose charge is less than the electron charge. Okay, but as I mentioned, we are not going to learn this. So for our case, electric charge is quantized, and the smallest possible charge is the electron or the proton charge, and that's why we call it elementary charge. Okay, and all other charges are integral multiple of electron or proton's charge. Okay, now I want to talk a little bit about ion. Okay, what is ion? Okay, so we can have two types of ion, a positive ion and negative ion. Okay, to understand this, let's go back to this simulation. Okay, so here you see that we have a neutral atom. Okay, so it's a carbon neutral atom. Now what happens if I add one electron? Okay, so if I add one electron, so you see that it is now negative ion, because we have now 7 electron and 6 proton. Okay, because it has more negative charge, that's why it is now, that's why we call it negative, carbon negative ion. Okay, so here you see that. Okay, now let me make it again neutral, and if I take one electron from the atom, okay, you see that it becomes positive ion. Okay, and positive ion because it has now more proton than electron. Okay, all right, so to understand more, let's consider table salt. Table salt is the combination of sodium atom and chlorine atom. Okay, sodium has 11 electron, and chlorine has 17 electron. Okay, I mean 11 electron and 11 proton and 11 neutron, I mean all 11. And the similarly chlorine has 17 electron and 17 proton and 17 neutron. Okay, so when you mix them, okay, to make sodium chloride or table salt, okay, what happens is basically sodium donates 1 electron to the chlorine. So sodium donates 1 electron and chlorine basically gain that electron. Okay, so when sodium lose the electron, it becomes positive ion. Okay, because now it has more positive proton than negative electron because it donates electron already. On the other hand, chlorine become negative ion. Okay, because it receives one more electron from the sodium. Okay, so the rule is when it donates, or when an atom lose or donates an one or more electron, it become positive ion, and when it gain one or more electron, it becomes negative ion. Okay, all right. The next thing I'm going to talk is insulator and conductor. Okay, so in chapter 15, you already learned about insulator and conductor, but that time it was for heat insulator and heat conductor. Okay, but the electric insulator and electric conductor are very similar to that. Okay, so the material that can easily conduct electricity, that are conductor, and where the electricity cannot be conducted easily, we call them insulator. Okay, very similar to the heat insulator and heat conductor. Okay, most of the heat conductor are the electric conductor too. Okay, so what is the definition here for electric conductor? Okay, so electric conductor allow charges to move freely within them. Okay, examples are metals, salt water. Okay, so what happen in metals? In metal, electrons are nearly free and easily move from one atom to another, and same thing happen in salt water. Okay, in salt water, it's not just the electron, it's basically the ion, positively charged ion. You already see that that becomes positive charge. Okay, positively charged ion, and these become negatively charged ions, and they can freely move in the liquid, I mean in the salt water. Okay, and what about the insulator? In insulator, charges cannot move or can only move with great difficulty. Okay, so here in this simulation you can see that. Okay, so here you see that the top one is conductor and the bottom one is insulator. Okay, so in conductor you see that electrons, the negative electrons, are freely moving within. Okay, on the other hand, in insulator, um, the electrons are closely bound to each atom. Okay, they are not free to move. Okay, all right. Now, what happened if we have a charged metal ball and a neutral metal ball, and they're connected by a metal object? Okay, so here you see that we have a charged metal ball, and here we have a neutral metal ball. Okay, and in the next picture, these two metal balls are connected by a metal pin. Okay, so when they are connected by a metal pin, you see the charge from the charged object moves to the neutral object. Okay, but if they're connected by a wood or an insulator, okay, you see that nothing happened. Okay, so you see that charge, I mean the conductor conducts charge easily from one object to another object. Okay, on the other hand, insulator cannot do that. Okay, and that's why they are insulator. And because conductor can conduct electric charge easily from one object to another object, I mean one metal, one object to another object, we call it conductor. Okay, and there are semiconductors too. Okay, so what is the semiconductor? Semiconductor have the properties that are in between conductor and insulator. Okay. Although semiconductor are very useful in electric industry, okay, electronics, I'm not going to talk about it. Okay. All right. Now here in this picture, you see that we can charge a neutral object by using conduction. So the method by which we charged it, we call it conduction. Okay. So we can charge an object by a method called conduction, and this is the conduction method. Okay. And there is another method, okay, by which we can charge an object. We call it induction. Okay. Now let me talk about induction. Okay. So induction, to understand induction, let's go to here. Okay. So here you see we have a conductor on the left hand side, and the right hand side we have a charged body. So this object has more negative charge than positive charge. Okay. So what happens if you bring it close to the conductor but don't touch it? Okay. So if I bring it close to the conductor, so you see that I'm not touching the charged object with the conductor, but here you see that when I bring the negatively charged object to a conductor, it pushes all the electron to the other side. Okay. Right. So if we now cut at the middle, one side will be positively charged, okay, and other side will be more negatively charged. Okay. So this is the method, we call it, this is the method of induction. Okay. By induction we can also charge an object. Okay. All right. I mean, we can, so here this object is charged body is negatively charged. We can use a positively charged also. So if I bring a positively charged body close to that, you see that it attracts the negative charge towards it. Okay. So then if I cut at the middle, the left side will be more positively charged, and then right side will be more positively charged, and left side will be more negatively charged. Okay. And this method is called induction. Okay, so we can charge an object by using conduction, and also by using induction. Okay, so the conduction is touching. So here we see the induction, and then here, or in the simulation, we see the induction, conduction and induction. Okay, non-conductor won't become charged by conduction or induction. Okay, but we'll experience charge separation. So here you can see that if you bring these positively charged, negatively charged, these, okay, so you see that this negatively charged body pushes the negative charge of the conductor on the other side. Okay, but for the insulator, nothing basically happened. Okay, it's basically distorted. Okay, so you cannot charge an insulator either by using induction or by conduction. Okay, the next thing I'm going to talk is electroscope. Electroscope is a device. Earlier days, we use electroscope to detect whether an object is charged or not, or whether it is positively charged or negatively charged. Okay, so here you see a schematic diagram of a of an electroscope. Okay, the important part is this gold leaf. Okay, the two gold leaves, and and uh, and this metal rod. Okay, and it is inside a container. It should be inside a container in order to avoid the contamination with air. Okay, so it could be metal or just a glass container. Okay, so here you see that metal and glass to see what happened inside, or it could be just something like this. So here you see it's a glass container. Okay, um, so you see that the electroscope, it has two gold leaf. Okay, and the gold leaves are connected in the metal rod. Okay, and then it is inside a glass beaker. Okay, glass container. Okay, now how it works? So you see that if I know whether this neutral object is really neutral or not, we bring it close to the electroscope, and you see that nothing happened. So if nothing happened, that means it is not charged. Okay, so if there is something happen, okay, so you see that the gold leaf is now away from each other, that means that object is charged. So the same thing for the, but in this method, it cannot detect whether an object is positively charged or negatively charged. So for example, here you see for both for positive and negatively charged object, it's separated by equal amount. Okay, so by looking at it, by looking how the gold leaf are going away from each other, okay, we cannot tell whether it is a positively charged object or a negatively charged object. Okay, and to understand, to know whether an object is positively charged or negatively charged, so we have to first charge it, okay, by using some known charge. For example, let's charge this electroscope by a negatively charged object, okay, by touching it. Okay, so when we touch it, okay, with a negatively charged object, okay, it is now negatively charged. Okay, now because it is now negatively charged, if I bring a negative charge, you see that the gold leaf repel more, right? You see that when I bring a negatively charged, the gold leaf repel more, but when I bring the positively charged, nothing basically happen. Okay, separation is very small. Okay, so that's how we know that whether an object is positively charged or negatively charged. Okay, so here both we have to use both conduction and induction we have to use to understand whether an object is positively charged or negatively charged, or it is neutral. Okay, all right, so I'm going to stop here. In the next lecture, I'm going to talk about some rules. Basically, I'm going to talk about Coulomb's law. Okay, and then the electric field. Okay, all right.